Hello, I'm Rahul, a junior doctor in the UK, and today we'll be discussing axis, how to calculate it and why it's useful. Now everything revolves around the wave of depolarisation, so let's discuss that first. Each one of these boxes represents a cross-section of the heart. When the cells are resting, they're generally negative. When they depolarise, they become positive, as you can see over here. Now in this example you can clearly see that the wave of depolarisation is towards the right. Now I want you to imagine leads as like speed cameras. If the wave of depolarisation is towards it, you get a positive deflection, which looks like this. If the wave of depolarisation is away from it, then you get a negative deflection, which looks like this. Now there are three limb leads you need to be aware of. Lead 1, 2 and 3. Now each one of these has numbers attached to it, but I think the easiest way to remember them for now is that lead 1 points towards your left, lead 2 points towards your left hip, and lead 3 points towards your right hip. We also have three augmented leads. These are effectively rehashed versions of leads 1, 2 and 3. AVL points towards your left shoulder, AVF towards your feet, and AVR towards your right shoulder. Now just to reiterate, if the R wave is bigger than the S wave, we have a positive lead overall. If the S wave is bigger, it's a negative lead overall. So now there are three leads that you need to remember. The three most useful ones are leads 1, 2 and AVF. Now one thing you have to remember is if that lead is positive, then the vector lies in the direction of that lead. So for example, if lead 1 looks like this is a positive deflection, so it lies in the red half. If it's negative, it lies in the opposite side, so it's in the grey half. Similarly in AVF, if it was a positive deflection, then it lies in the direction that AVF points to, so therefore it lies in the red side. If it's negative, it lies in the opposite side, which is the grey. This will all make sense once we do an example. Now before we do that, we have to understand this diagram on our left. Now the first thing I want you to understand is that the axis can be quantified. Lead 1 we'll refer to as 0 degrees, AVL is minus 30 degrees, and AVF is positive 90 degrees. Now there are numbers for each of the other leads, but I only want you to remember these three. The second thing I want you to remember is that normal axis lies between AVL and AVF. Anything towards the right is right axis deviation, anything leftwards is left axis deviation. Also remember, some people call this section here physiological left axis deviation, but that's not commonly used. Now let's begin the example. So in lead 1 we can see that the R wave is greater than the S wave, so therefore it's positive. Lead 2, the R wave is also greater than the S wave, so it's positive. So let's draw our circle. Now as we can see, lead 1 points this way. Since it's positive, we shade the same half of the circle. Lead 2 is positive. Lead 2 points this way, so therefore we shade the same half of the circle too. So we'll shade this side. As you can see, the overlap is over here, which matches the normal region. So therefore we have normal axis. Just to put that into numbers, remember it lies between negative 30 and 90 degrees. Okay, let's move on to our second example. So remember, the three most important leads are leads 1, 2 and AVF. Lead 1, the R wave is very small and the S wave is very large, so therefore this is negative overall. Lead 2 is equiphasic, so we'll skip that for now, but we will come back to it. AVF, the R wave is large and the S wave is small, so therefore AVF is positive. Now let's draw our circle. Remember, lead 1 points this way, so we're going to shade the opposite side since it's negative. AVF is positive. AVF generally points downwards, so therefore we're going to shade the same half. So we're going to shade this half. If we have a look, the overlap is this quadrant here, and this matches with the right axis deviation range, so therefore this ECG has right axis deviation. Now let's discuss lead 2. You'll understand why AVL is there in a minute. So lead 2 is equiphasic. Whenever you have an equiphasic lead, you should understand that the axis lies perpendicular to it. So therefore we'll call it A1 and A2. Now it could be either one of these. Now the way to work it out is to find the closest lead. So if we have a look at A1, A1 is closest to AVL. If we have a look at AVL, the R wave is very small, the S wave is dominant, so therefore this is a negative lead. Remember, negative lead means the axis points away from it. So therefore the axis points in this direction, so it can't be A1, it has to be A2. So therefore if we saw this on an ECG, we'd know it's right axis deviation. So this is another way to work it out. Now, why is axis useful? So there's three important things. The first one is hypertrophy, second is infarction, third is bundle branch blocks. So in terms of hypertrophy, you can clearly see in the first diagram that the right side is very hypertrophied. Therefore, the wave of depolarization is going to be more rightwards. So axis points towards hypertrophy. In the second diagram, you can clearly see that the left ventricle is infarcted. This is electrically silent, so therefore the wave of depolarization is going to be rightwards. So therefore the axis is away from infarction. The third one is bundle branch blocks. If you have left axis deviation, particularly more than negative 45 degrees, you should strongly consider left anterior fascicular block. If you have right axis deviation, consider left posterior fascicular block. Now, with left axis deviation, I want you to strongly consider left anterior fascicular block because this has a single blood supply. So therefore you see this quite commonly. Whereas a posterior fascicle has a dual blood supply. So even if you have right axis deviation, I want you to keep left posterior fascicular block low down on your differential list because this is a dual blood supply, so it's not seen very commonly. So that's the end of the talk. Thank you very much for listening. Please subscribe if you like this content, as there'll be more coming. Thank you.